Now we add convection and radiation to the model. Both convection and radiation are treated by Abaqus as interactions and must be defined in the interaction module. Convection can be defined in the interaction module by creating a surface film condition interaction or a concentrated film condition interaction. We will use the former. Abaqus prompts you to select a surface. This can be done in the viewport. In the Edit Interaction dialog box, leave the definition at the default of Embedded Coefficient. This allows one to specify the film coefficient in this dialog box. If the definition is set to Property Reference, the film coefficient can be defined as a function of temperature and field variables using a film condition interaction property. And if the definition is set to User-Defined, non-uniform film coefficients can be defined using a user subroutine. Specify a convection coefficient or a film coefficient of 13 watts per meter squared per degree Celsius, which is consistent with SI units and the Celsius temperature scale. Leave the film coefficient amplitude set to the default of instantaneous. Set the ambient temperature or sink temperature on this surface to 200 degrees Celsius, and leave the sink amplitude set to the default of ramp. Radiation can be defined in the interaction module by creating a surface radiation interaction for distributed radiation or a concentrated radiation to ambient interaction for a node or node set. We will use the former. Abaqus prompts you to select a surface from the viewport. Look at the Edit Interaction dialog box. For the radiation type, the choices are to ambient and cavity approximation. To ambient indicates that heat transfer is to the surrounding environment. Cavity approximation, on the other hand, tells Abaqus to approximate cavity radiation in three-dimensional models using uniform emissivity, a closed cavity, and an average cavity temperature. Choose to ambient. The ambient temperature should be specified in degrees Celsius to stay consistent with SI units. Set it to 320 degrees Celsius. Basic heat transfer courses or experience in this area will tell you that the emissivity has no units and must lie between 0 and 1. Assume that our copper block has a thick oxide layer, which is known to have an emissivity of 0.78. An important thing to keep in mind when working with radiation in Abaqus is that the analyst is expected to specify the value of the Stefan-Boltzmann constant, as well as the value of absolute zero for the temperature scale being used. Right-click on the model name in the model tree and choose Edit Attributes. Since we are using SI units, we set the Stefan-Boltzmann constant to approximately 5.67 times 10 to the negative 8th joules per second per meter squared per degree Celsius to the 4th power. And since we are using the Celsius scale, we set absolute zero to minus 273.15 degrees Celsius. If you don't specify the Stefan-Boltzmann constant and the absolute zero for your temperature scale, Abaqus will not run an analysis which includes heat transfer by radiation, but will issue an error message. At this point, we've created constant temperature boundary conditions on two faces of the block and applied heat flux, convection, and radiation separately on three other surfaces. You're probably thinking we will now define the remaining surfaces as being insulated, but we have actually already done this. If you do not assign a temperature or any sort of heat flux load or interaction, Abaqus assumes that there is no heat flow through the surface. Therefore, these surfaces are perfectly insulated. This is referred to as a natural boundary condition, and is useful if you desire a surface to be perfectly insulated, or if you would like to apply a symmetry boundary condition. Let's proceed with meshing the part. Since we have a dependent part instance in the assembly, we mesh the part in the part module. When setting the element type, we select both partitions at the same time by drawing a rectangle around the entire part in the viewport. We set the element type to 8-node linear heat transfer bricks. We'll set the approximate global size to 0.25, a coarse mesh for an actual study, but sufficient for our demonstration purposes. We then create a job named heat transfer job, give it a description, and run it. Abaqus informs us that history output has not been requested. We will tell it to continue with the job submission by clicking Yes. Let's view the results. By default, the plot state is undeformed, hence you see the undeformed block with the mesh elements in green. We shall display the temperature at the nodes. Go to Field Outputs in the Results menu. Change the output variable to nodal temperature at nodes. Abaqus displays the Select Plot State dialog box. If our plot state had already been a contour, it would have been updated to show the nodal temperatures. However, since the current plot state is undeformed, Abaqus asks you whether you wish to leave the plot state as it is, or change it to a contour plot. Choose Contour and click OK. You see the nodal temperature distribution on the part. Another way of doing this in Abaqus is to use the variable list in the Field Output toolbar. Usually we orient the part using the Rotate View tool. Abaqus does, however, allow you to view a part at a direction perpendicular to one of the coordinate planes, such as top view or side view. This will allow us to see the results a little better. Enable the Views toolbar by going to the View menu, expanding out Toolbars, and choosing Views. The Views toolbar is displayed on the screen. We can use this to better view and understand our results. Click Apply Top View to view the block from the top. The upper half, with the constant surface temperature of 400 degrees Celsius and the heat flux of 5000 watts per meter squared, is colored red indicating high temperatures, whereas the lower half is blue due to the lower constant wall temperature of 350 degrees Celsius and heat loss by convection and radiation from this region. The contours gradually pass from red to blue from end to end. However, you notice that the contour bands are not perfectly horizontal from left to right, but are curved. This is because we have heat loss by radiation from the left surface, hence the temperature drops faster on the left side than on the right as you move from top to bottom. Click Apply Right View to view the block from the right side. The area directly under the surface heat flux is the hottest. The contour lines on the right side of the plot indicate that it is hotter on the top surface than on the bottom surface as one moves from right to left in the region near the heat flux zone. However, once you reach the region with heat loss by convection, the contours bend the other way as the surface with convection cools faster than the opposite surface which is insulated. Aside from the default views, there are also user views marked 1, 2, 3, and 4. You can save any current orientation from the viewport by clicking the Save View tool. The Save View dialog box is displayed. You can choose which of the views you wish to replace with this new one. Let's store it in User 1. Change the scale and position options to Save Current. This will not cause the view to auto-fit to the screen, but will instead have the same zoom level as the current view that you are saving. Now if you zoom in and out in the viewport, you can return to the original view by clicking on 1. If you switch to another view like the bottom view or top view, you can once again return to this view by clicking 1. The Views toolbar, like any other toolbar in Abaqus, can hover in an undocked state over the viewport, or you can drag it into a dockable position by holding onto the blue ribbon at the top. You can also right-click on it and choose one of the docking options.